Sorry.
The speaker today will be Johannes Bausch from the University of Cambridge, and the title of his talk is From Variational Quantum Eigensolvers to Recurrent Quantum Neural Networks. Thanks a lot, Johannes, for joining us today, and we're delighted to have you. Please go ahead.
Thanks a lot for the invitation. Yeah. So I changed the title of the talk slightly because I wanted to give it a more gradual structure, starting from some more fundamental topics and then only going into quantum recurrent neural networks. So I hope that this will be accessible to a relatively broad audience. I'll start with a lot of classical machine learning. I'll introduce what recurrent networks do, and then I'll only later on go into more deeper topics. So the title is From DQEs to Recurrent Quantum Neural Networks. And the first 15 minutes or so, I want to talk about quantum machine learning by introducing my classical machine learning and talk about what a variational quantum eigensolver actually is. And I'll talk about a few applications. So this will just be background knowledge. And then I'll go into how to actually build a quantum recurrent neural network. I'll explain the concept of quantum neurons, which is very interesting because if you're familiar with neural networks, generally there's some type of nonlinearity in the setup, in the model that you train. And quantum mechanics is linear. So how do you get something that is non-linear into a quantum neural network? So I'll try to explain that. And I'll go on to explain what quantum recurrent neural network cell is, so what you apply at every step of ingesting a sequence, and then raise that to a sequence model. And finally, the last 10 minutes or so, I'll talk about applications for sequence learning and where I applied this. There were two interesting, more complicated tasks that I set this to. One is integer-digit classification, and the other one is how to address the question of how to model long sequences. In my case, I looked at DNA sequences with a certain structure, classifying those. Okay, so let's start with quantum machine learning. As a very broad overview over machine learning tasks, you can group them into three different categories. The first one is classification, where the task is to label data. Then you have regression, roughly speaking, predicting some scores. And the third task is clustering, where you try to create groups on multiple inputs. For classification, everyone knows how to classify cats and dogs. You just throw a deep neural network at it. There's also things like decision trees or even simpler logistic regression. And you can use this for spam filtering or things like handwriting recognition. And regression, on the other hand, you can also use deep neural networks for. Very simple model would be linear regression, where you're just predicting a linear trend. And you could use this for predicting stocks, say. Then clustering, on the other hand, is used, you can use something like k-means or hierarchical structures. And there's more modern variants that are used a lot in visualization of data sets, for instance, UMAP or TSNE. And yeah, what do you apply this to? Well, things like anomaly detection. So if your credit card company calls you and says, well, we might have detected some fraud, it's probably because you all of a sudden bought something that's anomalous and falls out of that cluster of what you usually buy. Right. So what models are used within what neural networks are applied for, say, classification and regression? So very roughly, you can find 5 different types. So the first type would be if you map one input to one output, then you have, let's see if I can use the pointer, then you have a model where one input goes to many outputs. The reverse would be many inputs going to one output. Say, for instance, a sentence to a sentiment. Many to many would be something like translation, and there's 2 different types of that. So one is you first ingest the entire sentence, the model does something, and then you output the answer. But if you, for instance, wanted to use that for live translation, you would need a model that looks more like this. Like one word comes in, one word comes out, and so on. So there's a bit of different structure there. Okay, so what does that actually mean? If you go back, the input coming in, and then there's this green block that does some processing, and then something comes out. What does that mean? Well, you can think of this as a graph in the following way. The inputs are weights, say a vector with numbers, S1 to S5. Then you have this connected structure in the middle, and you have these intermediate layers. They all carry a function, F1, F2, F3, and so on. And the way you transform from one layer to the next is given by matrix multiplication, W. So W is the connected edges here. And then you're applying this to the input, so the previous layer, which is just a vector. You're adding a bias. And then you're applying a function entry-wise, which is nonlinear. And that gives you the next layer. Right. So what we train is these two parameters, W and B. So every layer has a matrix with entries that we train and a bias that we train. The function is fixed, and obviously also the input, which is progressively passed through the network. Right. So if you go back to this model, you could think of every one of these blocks being one of these layers. So here there would be a matrix, here there would be a matrix. Obviously, you can make this much more complicated, where each of these cells themselves break up into feed-forward network structures. So this is the simplest setup. So what I've just shown you, that is a feed-forward network. Because you start on one side, you come out on the other side. So this very much looks like the one-to-one model. The one-to-many model, many models or many-to-one models are recurrent models, because generally you're reusing these cells. So if I'm drawing a graph like this, the weights of the matrices and biases in this block are the same ones as in this one and in this one. Same for these here. So you're reusing all the weights. And that's why it's called a recurrent model. You're recurring your cell. And to give you an example where this is actually used, I found a picture from Baidu, I think this is from 2018, where they used such a recurrent neural network for speech recognition. And it was a pretty big event because that model was stunningly good. There's now an open source variant by Mozilla. And what this model does, it takes wave data that's being pre-processed in some fashion, and it gives you the letters. So you just, you don't have to do any sophisticated algorithm prior to feeding your wave data into the network. It does almost everything itself. And this is a recurrent model because all these cells that do some processing are reused. In this case, it's a bidirectional recurrent neural network because information can flow both to the right direction and to the left direction. So it's bidirectional. Right, and in this case, it would be one of these many-to-many models where at every step you get an output. So you're not first ingesting the entire sequence, you're doing this step by step. So this would be useful for live translation. Right, so how does it actually work? Well, at every point in time, you block the input, the reported input, into some small window, say this here. Then this would be passed into the network. It's processed, then goes to these intermediate nodes. And they both feed the information forward as well as backward. And if you look closely, essentially, the weights and biases that you trained here are the same ones that you trained here, right? And then in the end, you would get the output. And the output for such models is usually a probability distribution over predictions. So say, for instance, if you order them just the alphabet, and at this step, it would be C with likelihood 81%. Great. So if you want to have a shorthand notation for recurrent models, since you're using the weights and biases multiple times in graph notation, you could say, well, the input at time t goes in, you're processing this, and then you're going to an output or a hidden layer, and you're also feeding that information back to itself. So every update is basically following the flow of these diagrams. And if you want to unroll this, which might make it more obvious what's happening, you're taking an input, putting it into the cell, feeding it forward, and so on. So what is this used for? I already mentioned live translation. You can also use this for speech synthesis, or if you want to label the action that's happening in a video. Sentiment analysis I've mentioned. So for instance, if I want to know if a tweet is happy or not. You can also use this for generative models. Now, the models are more complicated generally than just a feed-forward network. So each one of these blocks itself is generally made up of multiple individual components. So most fundamentally, a recurrent neural network would simply combine the vector that's passed from a past time step and the input into, say, a long vector by concatenating that. And then there would be a single feed-forward step with a matrix, bias, nonlinearity, and then it's broken up again into an output and the next step. So that is a very simple recurrent cell. That was the first ones that people looked at, just recurrent neural networks. Much better and much more sophisticated are LSTMs, long short-term memories, where the processes are broken up into a step that memorizes, a step that erases information, and so on. So like the structure should resemble what an actual learning process in your brain does. And there's another one called a gated recurrent unit, which is a tiny bit simpler, so it has fewer parameters, but it's so much more sophisticated than RNN. Generally, such recurrent neural networks are difficult to train. The reason for that is that long sequences where something happens very far in the past make it difficult for that information to propagate all the way to wherever your loss function occurs in the end. So this gradient decay over time is something that is really difficult to train and go around. Okay, so now we've talked about classical neural networks. Let me very briefly give you an overview over what a variational quantum eigensolver is, which is basically the analog of a classical neural network. So to recap, a classical neural network is basically a parametrized function family, where these parameters theta are the weights and biases, as I mentioned, and then you have a function f of theta, which is the application of the neural network to your data. A quantum neural network is quite similar. You have a parameter family, and they control how a quantum circuit looks. So they parameterize quantum gates. What you also have is a loss function. So you want to obviously train the neural network. So some target function, L, that you apply to, say, the neural network, applied to an input X, and a label L. X and L would be labeled training data. That's only one way of working with neural networks, but it's the simplest one, so let's stick with that for now. And then what you want is you want to minimize the parameters of, like, say, the average of that function over your training set. So S is your training set. Again, the loss function is applied to the prediction of the network and the label. And a quantum loss function is quite similarly defined. So again, you're minimizing overall parameters, and you have the same type of training set split into inputs and labels. Only here you have a quantum circuit U parameterized by theta, and the loss function can be something that depends on the output of the circuit and the label data. So how does such a parameterized quantum circuit look like?
Sorry, can I ask a quick question?
Yes.
So I should think this output is a classical output that we're trying to match?
That is free to use. So for instance, you could say I'm measuring the output of the circuit, and then I'm doing this multiple times to get some histogram over outputs and feeding that into the loss function. That
Okay,
would be
but
one way.
if there's sort of a distribution over classical outputs, it's not that I have a quantum state I'm trying to match and doing some sort of fidelity.
Not necessarily, no. But you could conceive of a loss function that is itself a quantum circuit. That would be possible too. And then you could feed in a quantum state and measure only in the end.
Yeah, great. Thanks. And my second question is that, I mean, you're calling it a quantum neural network, but this also looks very much, as you said at the title of the slide, as a setup for sort of standard VQE. And so how should I think of, how should I think of quantum neural networks as not just another description of sort of the standard VQE approach?
Yeah, so I actually have a bit of, I don't like the terminology that's used at all. So VQE, variational quantum eigensolvers, are what people call quantum neural networks. I don't like that very much because I think neural networks are more generic. Like VQE is a very specific type of circuit generally, but people call those neural networks. I actually think that the terminology is poorly chosen. Yeah, so I apologize for this. I think maybe I should refer to that as VQE in general when I'm talking about these parametrized circuits. Maybe I don't actually know what a good definition for quantum neural network would be.
Okay,
yeah,
great.
Yeah. Yeah, no, I'm happy that people call me out on this as well because I don't like the terms. Yeah, or talking about unitaries as connected layers and so on. There's a lot of trouble with that, I think. Anyways, thanks for the question. So yeah, so let's talk about variational quantum eigensolvers or parametrized quantum circuits, quantum neural networks, so to say. So an example where you would want to apply this is, say, I want to approximate the ground state of a local Hamiltonian, so like a condensed matter system, right? That would be useful in quantum chemistry or material science. So you use a parametrized quantum circuit, U theta, you apply this to some initial state, and that gives you a state that's parametrized by theta, right? So far, so good. Now, what does the loss function look like in the label? Well, the loss function in this case, because I want to minimize or approximate the ground state energies, I want to minimize the energy, would simply be, I'm taking a local term, hi of my Hamiltonian, right? So this is just a sum of local terms, say in an Ising model or something, an XX coupling. And I am calculating the inner product. I can do this, for instance, by performing tomography on this state and then doing this classically, if you have that matrix classically. You could also do phase estimation on hi. There's multiple ways of extracting that as a number. But let's just assume for now I can perform that calculation efficiently. Then I'm just calculating that number and I'm minimizing that loss function. So that would be my goal. I want to minimize over my parameter space the expectation value of the energy of that thing. So I would have a loss function that's then a sum over all hi. And that would minimize the energy of the entire Hamiltonian. So that would be a very simple application. So you take a quantum circuit that parameterizes a state, that's an ansatz for your energy minimization problem. Great. So what do they actually look like? Well, the simplest one that you could conceivably write down is if you just had a qubit. So say this is just in C2 or so. Then I'm taking a rotation of that qubit, which carries 3 angles. So just think of rotating on the Bausch sphere. And I'm getting out another qubit. On 2 qubits, I could think of adding entangling gates, like a C0 gate here or here, and then interleaving them with parametrized gates. This is the general setup. So what you do generally is to parameterize the single qubit unitaries, not the 2 qubit unitaries. And the reason for that, I guess, is because single qubit unitaries are actually easier to implement on many quantum hardware, many actual quantum devices, whereas parameterizing a continuous family of 2 qubit gates is much harder. So I can conceivably do a U3 gate on any angle pretty quickly on a quantum device, but say a small angle ZZ rotation between 2 qubits, that's much harder. So this is why these circuits generally look like this. And you can make this much bigger, obviously. So again, as a summary, so you're interleaving the fixed entangling gates, C0 or CZ, with parametrized single-qubit unitaries. That's the generic setup. And applications for BQE, as I said, is ground states. You can use that for simulating fermionic systems, time dynamic simulation. You can load data. So you can train the circuit to produce a state that represents a distribution that you would like. You can also calculate excited states. Okay, great. So much to that. That's mostly background on classical and quantum machine learning. If there's no questions at this point, I'd like to come to the quantum recurrent neural networks. And I'll start out with talking about the quantum neuron, then a quantum recurrent neural network cell, and then build that into a recurrent model. So what's the motivation here? Why would we need a quantum neuron? You have BQEs, you know, they kind of perform in some aspects for some problems. If you look at traditional BQE circuits, they have a very high parameter density. What do I mean by this? Well, in comparison to a feed-forward network that we had before, where you have matrices and biases, as I said, here you have these angles. If you think about what you can do and how finely you can control the activation of a single such node in a classical neural network, you have a lot of control over what's happening. So say, for instance, I would want the output of this node to always be 0. I just add a huge bias. And that would mean that the nonlinear activation function or so is either always 0 or, depending on what it is, always activated. Here, if I want this entangling gate not to act, so I don't want these two qubits to be entangled at this point, I have to pick these 4 gates in a very specific fashion. You can actually do this analytically, and it will only work on certain inputs. So you can't really disable the C0 for all inputs. That's a problem. So with regards to the level of abstraction where we're working, the parameter density is extremely high in the BQE setting, and pretty low in the classical neural network setting, right? Another way of thinking about this is we're acting on bits for BQEs. And every bit now has a lot of parameters to work with. Whereas down there, we are actually working with floating point numbers. You have arithmetic, so there's a lot of layers of abstraction. Right. Another way of seeing this is that the traditional BQE circuits, they have a lot of entanglement pressure. It's like you're starting with the initial state, which is product, and then you're saying all of a sudden, well, you know, apply this ridiculous wall of entangling gates, then okay, so we're rotating again, then again, ridiculous amount of entangling gates and so on. There's a lot of stuff happening. And it's not clear to me at all why that would be beneficial to an ansatz for a circuit. So quantum neuron tries to circumvent this by adding more structure to your parameterized quantum circuit. So if you start out with a rotation gate, this one, so this is a rotation around the y direction, so this is a Pauli y. If you express this as a matrix, it's actually a real matrix, and it's simply cos theta, sine theta, and so on. I can now add this in a controlled fashion in a circuit, as in I'm performing a controlled rotation. Then I'm applying this gate here, which is a controlled IY gate. I'll write out what the action of that is in a second. And then you're undoing the rotation, also in a controlled fashion. And then this here means post-select on 0. Okay. Then what is the action of this circuit? Well, let's start out with an initial product state where the top lane is simply a qubit in state 1. So this would be, say, 1. Okay, and the other ones are in state 0. And the first controlled rotation, well, this is 1, so it always acts. So it simply rotates the second lane to cos theta 0 plus sine theta 1. The third qubit is not involved in this step. The next step is you're doing a controlled IY gate, which simply flips the phase of the second qubit depending on the first qubit being in state 1. So this is basically a controlled phase gate. But you're also flipping. Right, so in addition to the phase, you're also flipping this to 1 in a controlled fashion. Right, okay. Then if I undo the rotation again, I'm getting these quadratic coefficients in here, right? So cos squared theta, then cos sine, then minus sine cos, and then plus sine squared, and so on. Okay. The last step, this is the post selection. I'm simply canceling everything that did not have a 0 in the middle, right? So if you color the states that have this property, this one has a 0, this one, sorry, middle one. This is actually, I want the 0 here, exactly. I think this is actually wrong, sorry. Exactly, I don't know, it's not, 0, 0, this is 1, 0, 1. Something is wrong, there's 2 0 1s here. We should get this correct. Does anyone spot the mistake? 0, 0, 0, 1, 1, 0, 1, 1. Is that right? This is 1, 1, 0. This is 1, 0, actually. I think that's right. Okay, so which ones do we have left? It's this one and this one. All the other ones have a 1 here in the middle, so we post-select them away. What's left is cos squared theta plus sine squared theta as coefficients. So you can go, I'm not entirely sure if that calculation is correct. If you want to do it, I'm pretty certain that's what comes out. The normalization is simply the square of the coefficients now. Okay, great. So what we have now is a circuit that has a nonlinear dependence on theta in the sense that, well, you get coefficients that are not just rotations of theta like the first thing, but it's actually squared of theta. That's interesting. So we'll come back to this in a second.
Can I ask a quick question here?
Yes, definitely.
So if you're going to use post-selection, I mean, for one neuron, I understand, but then if I put together a bunch of neurons, it seems the probability that I get the post-selected output I want is going to be very low. And so I don't understand how this is useful.
Yeah, no, that's an excellent question. So post-selection is bad, right? If I do this multiple times, I get an exponentially falling off probability of success. What do? Well, you do, you do amplitude amplification. So what you do is instead of post-selecting, you apply this circuit and then you do fixed point amplitude amplification to amplify the probability of actually measuring 0 up to almost 1.
But that's
actually an interesting,
more than just quadratically. You can actually push that up to some constant.
Almost. So you would no. So fixed point amplitude amplification allows you to. So the outcome here. So what I want to post-select on is these two states, right? So the one with the 0 here and the one with the 0 here, and they have weights, coefficients cos squared plus sine squared of theta. So the probability of measuring this is actually simply cos squared theta plus sine squared theta, right? So that's the probability. And then with fixed point amplitude amplification, I can get this to 1 minus epsilon in a few rounds, essentially.
Great, thanks.
That's a very good question. And I'll come back to this later. So I monitored the overhead that you would need in terms of amplitude amplification for that reason. Great. Okay, so just to summarize this quickly, so it does require post-selection, right? So that is a valid concern. It performs a non-unitary amplitude transformation, right? So that's what I meant earlier, not non-linear. It's non-unitary in essence, because the post-selection is a linear projection. And the entire process only has real amplitudes, which is also nice because it makes implementing this in a simulation much easier. So the quantum neuron, you just build in the end is iterated. So if you call this entire circuit n, which you would apply in this block here, you can also iterate this once more. So that means you apply the neuron, again you do your controlled phase and bit flip, and then you apply the inverse of the neuron, and then you post-select again. So every one of these has a post-selection step. So it's a very valid concern that post-selection might blow up. Post-selection here as well. If you iterate this, what happens? Well, instead of a non-unitary transformation that just gives you squares, now you have higher powers of cos theta and sin theta. If you calculate what this function actually is, with the coefficients, you get the following expressions. So f of theta, which is the coefficients, is an arctangent of a tangent to a power. And that, obviously, I didn't know what this looks like, but in effect, what this does, it creates a thresholding function. So instead of like a nice cos curve with respect to the input angle, you get very steep ones with flanks that almost instantaneously ramp from 0 to 1. So this is the type of activation that you would want in a neural network, where you have like a type of plateau and then a steep intermediate region where the gradient is large. So for instance, used in classical machine learning a lot are sigmoid functions that look a bit like this, right? Where you have a steep section and a flat section here. Great. Obviously, I can take these quantum neurons and chain them, so I can have multiple ones behind each other. So in particular, what I'm drawing here is what I haven't talked about yet. This can be not only a single qubit, it can be n qubits. And you could control on, say, the first qubit, you can control on the nth qubit. Each one of them carries its own angle. And then the overall action on the output lane is that you have the input untouched, that's the control lane. That's the controlling lane. And that's the output. And you're rotating by an angle eta, which is simply the sum of all the individual neuron angles, weighted by whether or not that qubit was on or not. So xi is either 0 or 1, depending on whether the ith qubit is 0 or 1. Right, so in that way you can make an affine transformation of the input angles. Right. You can make this even more complicated. What if I now make these rotation gates not only controlled on a single qubit, but on 2, right? So if I'm abbreviating this as this overall gate, then the transformation you're getting, this angle eta, is now not only an affine transformation, which would just be this part, but you're also getting higher monomials. What's interesting about this is you can actually create logic gates in this way, right? Because xi, xj is equal to an and of xi, xj. And if you're looking closely, obviously I'm talking about this is if it was bits. I'm going to talk about what happens in superposition in a second. But just treating xi and xj as 0 or 1, this is very interesting because you can create logic gates in this fashion. Right, okay, so this is the quantum neuron, and we see it creates a very, very interesting non-unitary transformation on the output lane depending on the parameters. That is the goal. It's a higher, a more sophisticated version of a parametrized quantum circuit. So let's now try to make a QRNN cell out of this. So again, a very brief reminder, what we want is, we want to find a building block like this, let be A, that if applied repetitively, translates some input to some output. And to do this, this is my setup. So this is the recurrent neural network cell that I came up with. And let me explain what exactly these stages are. So we've already seen the recurrent cells and the quantum neurons. So this here is a quantum neuron. This one as well. So you just have multiple ones where the head here, that's the output. And these here would be the controlled lanes, right? I'm just reusing them over and over. There's some interspersed single qubit rotations. But overall, the entire cell is basically comprised of quantum neurons. The input word comes in through a classically controlled set of bit flips. So all this does here is it flips those bits that you want to set to 1. If you now look closely, all of these lanes here, they're always only being controlling. They're never acted on. So in particular, this means over the entire action of the circuit, we maintain a product structure between the input, which is product, it's a basis state, and the cell state, which is the hidden state, so to say, or recurrent state. That's nice because that means we can undo the input word. So this is just a reset here. And then we can reuse these lanes and write out with a set of neurons the output of our recurrent cell. And then we measure this, right? So here we measure the output. Yes?
Can I ask another quick question? I apologize. I'm a little confused. If you have those control wires, I mean, you're not affecting them, but you're inducing entanglement between the control wires and the top wires. So in what way can you sort of undo that computation and using them again if you've already got entanglement between those two things?
That's a good question. So the I/O lanes initially are in state 0, right?
That X there doesn't do anything to them to...
So this here, if I just look at the input lanes, for instance, the state could be 0, 1, 1, 1, 0, or something like this, right?
At that point, you're not in linear superposition. You're in some product state.
Just some product state, not in superposition.
Then I understand. I was confused. I had thought at the point where your 0, 1, 1, 1, 0 was, you could potentially be in a linear superposition.
No, yeah, exactly. So it's designed in that fashion, right?
That makes sense to me then, thank you.
Right, okay, so you go in there, you can reuse the lanes. So here in particular, you would be back at 0, 0, 0, 0, 0, and so on. Here, obviously, now this here would be entangled. Right, so this is generally entangled. Because, as you're saying, if the control lanes are in superposition, you're creating entanglement between what you're acting on. Great, so how does that, how can we reuse these cells later on? Well, if we measure, we collapse this entanglement again. So in particular, we collapse the internal state of the recurrent cell, as well as the measured output. And this is actually an interesting effect if you think about this. So if the neural network that you're applying recursively or sequentially, at some point you're measuring an output probabilistically, say a predicted letter A, you're also collapsing the internal state of that network at this point, meaning the network knows what you measured, and it can adapt the future predictions depending on what you measured. And this is something that classical neural networks cannot do, because the output is simply a set of numbers. You measure them out exactly. Just as a side note. Okay, great. So now we have this recurrent cell. which is mainly made up of neurons, a few input-output gates, and a few single qubit rotations. As you asked earlier, indeed, the neurons are implemented by using fixed point amplitude amplification, so you don't have an overhead in terms of post-selection. So you can actually apply these neurons. Now let's combine these cells as a recurrent model, and that's as simple as just apply them sequentially, right? So that would be the first input. That's the first output. And that's the second input, and so on. So essentially, this entire block here would be the first stage. You're starting with something initialized to 0, like the hidden state is also initialized to 0, and it's just applying this over and over again. So the model is exactly what we saw in the classical case. You're mapping classical inputs to classical outputs. Right. So your repeated application of the same subroutine makes this the recurrent model. That's just the summary of what I just said. You have a set number of input lanes. You read from these input lanes. You work on that with the hidden lanes that have access to the input lanes. You reset them. You write that to the output, and you measure them. Right. Okay, so now we've defined the model. That's a recurrent quantum neural network. Let me now pretty briefly go over applications. Just to show you if that actually worked. So how could I implement this? Well, I used Torch, and the fact that the entire model has real amplitudes made this relatively simple. There were a few shortcuts that I was taking. I was not actually implementing fixed point amplitude amplification, because if I have the matrix in the state exactly, I can post-select. I can just project on that state. But I was monitoring the overhead of post-selection just in case to see, could I conceivably implement this on a quantum device? And yes, you can. I can show you graphs about this later. You can train relatively large circuits with this. So I was quite surprised that Torch could handle, like the resulting quantum circuits that come out of this have depth of like hundreds of thousands of gates. And I could go up to like 12 qubits or something like this. But obviously the length of this entire circuit would grow linearly with the length of the input. But I was extremely surprised how powerful Torch was in terms of doing back propagation through these gates and giving me like a gradient, applying Adam and so on. It's really optimized. In Qiskit, which was my first attempt, no chance. Okay, so for sequence landing, which is simply, you're trying to learn a sequence by heart. I had the very simple task of learning whether the sequence was just 4, 4, 4, 4, 4, or 1, 2, 3, 1, 2, 3, 1, 2, 3, and so on. And I use this to assess which optimizers are actually good for this recurrent neural network. And the top three lines, the blue one, the red one, and the green one, are ones that are used traditionally in classical machine learning. So stochastic gradient descent, RMS prop, or Adam, which is versions with momentum and instead of just doing stochastic descent. You can see that the learning rate, for the models is quite different, so you have to be careful what you pick there. That's as in the classical settings, you have to do a bit of hyperparameter optimization. What was interesting is that a gradient method that's generally used for VQE did indeed perform faster, much better, LBFGS. However, since it takes, I think it approximates the Hessian of your circuit, it was extremely slow. So generally, you don't want to use slow optimization methods, even if they're better, because you're not interested in finding the global minimum. If you do machine learning, what you're interested in is a relatively flat minimum somewhere, you don't really care where it is, that generalizes well. So if you find a really steep or a deep minimum in any of your machine learning tasks, you're doing it wrong. You're overfitting your data. Right. Okay, next task, learning XOR sequences. What's that? Well, it's just a sequence of bit strings, and you're trying to predict the every third letter based on the previous two. So 0, 0 should go to 0, 0, 1 should go to 1, 1, 0 to 1, 1, 1 to 0, and so on. So this would be a sample sequence, right? And as I said earlier, the interesting thing really was you can do logic. So you would kind of expect these quantum neurons to perform well on this task. And indeed, it's not a problem at all. Like, learn these sequences, you need very, very few steps. And I used this task to optimize what initialization I should use for all the parameters in my model, right? So the neurons, they carry ingots. How should you initialize them to get good training performance? You can also add biases. That was the single qubit rotations that I was pointing at some point. Yeah, and you get heat maps. So you can do that type of analysis. I'm just showing this for completeness. Right. Okay, something a bit more interesting would be integer classification, which simply asks the question: if I give you a picture of zeros or ones or threes or something like this, predict what number this is, right? And what's the data really? Well, it's a picture of 32 by 32 pixels, gray values, and I'm feeding this in sequentially. So what I'm doing is I take the first pixel, I discretize it to say 3 bits, and then I'm feeding this in. This is not generally how you do image recognition. I'm just pointing that out. You can do this. I use this task because people have studied this with classical neural networks and also with quantum neural networks, this specific task. So I could have a good comparison. You would normally use convolutional neural networks or something like this for a task with images. Anyhow, so how well does that do? If I train a 12 qubit model with Adam, that gives us about 1,500 parameters, and I don't augment the data at all, so just feed it in step by step. I get an accuracy of over 99%, so that's pretty good. Better comparison is people have actually done this with variational quantum eigensolver on 17 qubits, but they did remove the ambiguous samples. They got 98% probability. That I was not sure exactly what it meant. You can read this up in the paper. It wasn't quite clear to me what exactly that meant. I think it is because they downsampled the pictures and discretized them to just 2 colors. There were some samples which were in both classes. I think that's what they removed. Right. If you use the same neural network that we used before, the performance is actually worse than in the single qubit, in the 0-1 case. And I think this is simply because the letters are more equal. However, now if we use a different training method, and we also use an ensemble of them, so ensemble learning is something that you also do traditionally. You just take a group of experts and you let them do majority voting. You get back up to 99%. And full MNIST, where you do a bit more sophistication before you feed the data into your recurrent neural network. In my case, I used UMAP, which is a clustering algorithm, unsupervised though. And then you take the coordinates of this mapping, of this clustering, you discretize those and feed them in, you get a much higher, or like comparably high performance again on all digits. Okay, so how does that compare? An LSTM, which are pretty standard, pretty state-of-the-art recurrent neural networks, classically get like 98% if you do this pixel by pixel. Right. There's a variant with a variational quantum eigensolver, which was not so good. The task there was just simply to guess if the digit was even or odd. Then there was a proposal which was only done theoretically, which is based on quantum slow feature analysis. But it requires a lot of qubits, it requires QRAM and so on. And also the output was not as good. Right, so we get not competitive, but good performance on integer classification, which is kind of nice. You can also generate digits. So if you turn the task around, you start the classification, you output a picture, it can generate digits for you. And then the last application that I want to talk about is, as I said earlier at the beginning, if you have a very long sequence, these recurrent models struggle because the gradient kind of vanishes. And this has been an open question in classical machine learning for a long time, how to circumvent this for recurrent models. There's been a period where people were suggesting that the recurrent cell should be orthogonal or unitary, which I found interesting. The reason for that is because a unitary operation does not diminish any of the eigenvalues. You're just rotating, right? All the eigenvalues are on the complex circle, radius 1. So you're not losing any eigenvalues. You're just rotating them. And people have tried to figure out a good parametrization of this unitary recurrent cell or orthogonal recurrent cell, but they haven't thought about quantum circuits. And I think in that setting, the motivation to circumvent this gradient decay problem with unitary recurrent cells is very natural for us if we work in quantum computing, because the transformations are unitary by design, more or less. Right. So the task that I was looking at to compare the performance of this is you have a DNA sequence where you want to predict what's the letter following the single G base. So, right. So you have this base G here, and then the question is, what's the next letter? And these sequences can be very long. The samples that are generated always had these single G letters in the first half. So if you look at sequence lengths of, say, 500 or something like this, it means that G was at least 250 applications of this recurrent cell in the past before you actually want to know the output. The task was, I'm ingesting the entire sequence bases, and at the very last step, which the neural network also had to learn by itself when that happens, give me that base that followed G. So the gradient, the loss function had to propagate through the entire 250 or 500 applications of these cells to get to that point. And indeed, the unitary nature of this QRNN meant that the cost of training did not increase. In contrast, an LSTM does increase quite drastically. So this is a log scale. So it actually, I'm not saying it blows up exponentially, I'm not quite sure. This is all empirical data, but it grows drastically. And a traditional recurrent neural network is really difficult to train. The reason why this caps out here is because I stopped a few of these runs because they were going on for days and couldn't find the data. So yeah. Okay, so that's good news. They actually solve a classical problem in a sense. Even if you simulate a quantum circuit with a classical computer, it gives you something. I found that quite intriguing. Okay, let me give you the summary.
Can I ask a very quick question about that?
Yes.
First? So can I interpret what you're saying is the optimization of this doesn't have a barren plateau problem at all, or is that the wrong message to be taken?
That's actually also a very good question. So there are these results about variational quantum eigensolvers circuits, parametrized quantum circuits that have barren plateaus, right? So you make the circuit steeper, and then all of a sudden the gradient is so flat, like it falls off exponentially in these circuits. So that's bad for training. On the other hand, in classical machine learning, you want the recurrent cell to be unitary because it solves the gradient decay problem. I'm actually not sure why there is such a
disconnect.
Yeah, there's two poles to the problem, two sides, which I find very intriguing. And that's actually a question that I would like to address more formally. The only thing I can think of is that the structure of these recurrent neural networks it's more or less designed in a certain fashion to to get nice gradients for certain tasks, right? So the recurrent cell really
You don't have an arbitrary light cone. You don't have a light cone that's spreading for your...
Indeed, yes.
You might have if you just had a brick pattern of gates, and maybe that's saving you here.
Indeed, right. because you're like these BQEs, they explore the full space of SUN really quickly, right? I mean, you're like, there's so many parameters, you're really going everywhere. But that's not the case here. Yeah, that's a good point.
Great, thanks.
Okay, so to summarize, we have a higher level parametrized quantum circuit. Would be interesting to see where else we can apply this, not only in the recurrent setting. Very few parameters create higher order activations. So one thing which I haven't pointed out is, it's quite obvious, since I'm in these quantum neurons, you're using at the same angle to do a controlled rotation and undo it, you're actually reusing the same parameters over and over and over again. Like if you make these relatively deep, the same parameter comes up like a lot of times, and then you're also applying the recurrent cell over and over again. So there's so much reusage of parameters. It's good. The performance is comparable to classical in some instances. I'm not saying this is state of the art at all. Like MNIST is, you can solve this much better, as I said, like with convolutional neural networks. You can actually simulate these networks on a classical computer, like the machines that I ran this on were not GPU based even. It's like, I think the biggest machine I needed was like 16 CPUs and I don't know, like 30 gigabytes of RAM or something like this. So it's not even by no means large. And then, yeah, I did some benchmarking, which showed interesting regimes for initialization and so on. And curiously, like cheap methods like Atom work relatively well. I think in the end, what you would want is, if you're looking at BQE circuits, the reason why you need quite sophisticated training algorithms is because the minima are quite steep. There's a lot of them. If you start over parametrizing in a sense, then that flattens minimas. And you want that. You want to have gradients that are relatively flat, you know, large values that are very broad. That's what you want, and that's what these huge models that are nowadays used in GPT-3 or something like this, that's what they do very well. Like the minima are relatively equivalent, so it doesn't matter which ones you find, and there's a clear gradient direction from the initial setup to the end. Okay, so the outlook would be, well, can you make a more optimized implementation to get bigger quantum circuits? Do more benchmarks. Someone was suggesting pen tree bank to get a bit of semantic modeling in there. More arithmetic to get, you know, see if it can actually memorize numbers and then do the operations, then spit out an answer. And then maybe study ensemble learning. You can also do this in other tasks. Yeah, cool. That's everything from my side. Thanks a lot.
Thanks a lot, Johannes, for the very interesting talk. Are there questions?
Can I ask one more quick question? So you have a very special structure for this circuit, for this QRNN. Is it sort of transparently obvious that when the number of neurons sort of goes large, this is not going to be classically simulatable, that this really is benefiting somehow from quantum advantage?
That's a really good question. I haven't thought about it, so I'm trying to come up with a good answer on the spot. The fact that it's only real amplitudes doesn't really do much.
That shouldn't affect you, but nonetheless, the structure is very special, right? And so you could imagine.
It is very special. No, indeed. Good question. Leave it there. No, I think one interesting thing would be to study entanglement entropy between, you know, like these hidden cells. Like how much entanglement are you actually creating? That could give you a hint on how well you could represent these. Could you model that with an MPS over time?
Even a numerical answer to this question, where you just run tensor networks on it and see if it.
Right. Yeah. Do you think that the tensor network algorithms are sophisticated enough to, you know, pick up on that structure? Essentially, is that what you're? Yeah, I guess.
If it's low entanglement,
that is a good question. Yeah.
Sure. It's true if the entanglement blows up, or if there's some large entanglement between some qubits but not others, then it may not sort of. I mean, it's not going to like reorder things and pick up on that aspect, but would at least be a zeroth order.
It's true.
Instead of answering that.
No, that's a really good question. That's something to study, actually. Yeah. I wonder how difficult it is. But yeah.
I mean, the other thing is that maybe you can figure out how to embed sort of just a general circuit into this special structure, given enough.
Oh, you see, like expressivity of the circuit model. Like,
if
like
you
actually
embed
model something.
an arbitrary circuit into it, right? Then you would prove that it
Right.
has formal quantum advantage.
Yeah, that's good.
Staring at your structure.
So I did. So that's a question I actually answered. So the expressivity is such that you do cover all of SUN. So it is universal because you can set a lot of these parameters to 0. All you're keeping in every neuron is just one single controlled rotation, which is basically a ZZ or something like this. And then you still have these interleaving single qubit rotations. So you can set the parameters so that what you're getting out is just a VQE circuit.
Okay.
One of these
so at least in its highest generality, you can get anything out.
Right, in general. Yeah.
Can I ask a follow-up question on this? If I switch to quantum data that I want to process with this, do you think that would be a viable ansatz to get an interesting algorithm?
That's a really good suggestion. It would break the fact that the input lanes are unentangled with the hidden state. Right. So that is an issue. So you would have to redesign that bit. But conceivably so. I mean, the question is also, what do you want the recurrent network to do on superposed inputs? Do you want it to just, I guess at the moment, if you just applied this, you would in a sense get, you would collapse your input data as well. Do you not want this? Then you need to do away with these intermediate measurements in a sense.
Oh, so I would lose entanglement with some reference, say, or
right.
Yeah, right.
You could obviously postpone all the measurements and then do something more sophisticated with the output as well. Also, one thing which this does not, so this just gives you product output if you so want, right? Because at every point you're just measuring, you're getting some classical data out. The question is also, if you put an entangled input, do you want an entangled output or do you want sequence output? That's, I guess, there's a lot of questions. And if you have the framework, then maybe you can design the model to work that way.
I mean, I guess the application I would be interested in is kind of producing interesting entangled states, right?
Right. Yeah.
And kind of manipulate, like like in the channel coding thing where we use the classical machine learning ansatz, but kind of just switching to a quantum machine learning ansatz here.
So one thing which you could do is, if you don't want to reuse the I/O lanes, don't measure, right? So just keep them around and take a new set of input lanes at every point. Then at least you're getting an entangled output over time. So that works. Then you could do something more sophisticated with the output, but still for classical input, sequential input. So.
Mm-hmm.
Can I ask a follow-up question? So, sorry, I had limited understanding of this. I'm a stupid experimentalist, but I like your example of trying to do basically number analysis and identifying these different states. So connecting that with what Felix just asked, I'm wondering if this is a way of getting basically state analysis, state discrimination. So you have some complicated states and you want to feed them in and tell which of the class of states does it go into, because you're trying to characterize something going on the network and you want to be able to distinguish some set of fiducial states. Is this, it seems like that would kind of be the thing that this might be able to do.
That would be, again, like if the input is entangled, the current setup doesn't really work, but that's definitely something that you could conceivably do.
Well, the states themselves might be entangled with each other, but it's still, there's a box around it. It's not that I'm sending you something which is entangled to something outside. I agree that that's right. But you could imagine sending these states that are 10 qubits across and they're entangled in some bizarre way. And rather than doing a whole tomography, I want to come up with some better way of distinguishing. And my understanding, again, I don't really know much about this, but my understanding is that in general, state discrimination is a hard problem as you get to states, right?
Yeah, no, that's true. So your proposal is basically take the state, feed it in qubit by qubit into the network and let it try to figure out the classification in a sense. That would be so again, if you change the setup in the following way, that the input lanes are not reused, right? So you just like start out with 0, then feed in your qubit initially, and then carry the output away and take a new set of input qubits and so on. That would be possible with this recurrent neural network. And indeed, that could be something that answers state discrimination. If your loss function is such that you know, like say you have two classes of states and you want to distinguish between the two classes, then you just look at the last output. So the recurrent neural network spits something out, and the last bit is like either 0 or 1 or something like this. And then that is your loss function. It's conceivable that that would work, indeed. That's a good suggestion, actually.
So you mentioned classes of states, and I was originally thinking states instead of classes of states, but I'm wondering now whether or not this is also a way of doing some sort of a entanglement witnessing or dimensionality witnessing, because in some sense those are different classes of states, right? Whether the things in n dimensions or n+1 or something like that.
Yeah, maybe you're right. So I mean, you could start with just states. So give me some, but I guess essentially the thing must figure out a basis in which to distinguish these states, right? And if you have classes of states, that might be simpler because you just need to like find a hyperplane or something like this. Right. No, I think these are really good suggestions, actually. I really like them because I was looking for more applications for this, but I haven't thought about that. State discrimination is a really good one. I like that. I'll think about that more.
If you become rich and famous, send me $1.
If you want to talk about that more, I'd be very keen to, actually.
I mean, I'd be happy to, but it's actually, we should fold in other people who probably know a lot more about it. I mean, I know about the difficulty even on like 2 or 3 qubits, because we've tried to do experiments with that. You know, doing much more general things. I'm not the I'm probably not the expert at UAUC on it, but yeah, I'd be happy to talk a little more.
I'd be interested in that too.
Great.
Yeah.
Good.
Yeah, awesome.
Good. Someone who actually knows what they're talking about. I know enough to be dangerous.
I have a question. So you mentioned your the parameter space of the quantum neurons is much larger than that of your classical neural networks. So is there going to be a scaling problem of applying these to large quantum computers and implementing such quantum neural networks in large systems?
I think the scaling is quite efficient. So as I said, the number of qubits that I had in the samples that I did for say MNIST or so was 12 qubits, which is relatively small. The circuit depth is quite deep, so they're very deep circuit. This is definitely not a near-term algorithm. The post-selection overhead actually grows a bit when you need more qubits. So to answer that question, you can prove that it doesn't grow more than linear in the number of qubits, so that's not bad. I think this is something that you could conceivably implement. The only problem is the way I implemented it, I was actually, because I was doing sequence-to-sequence learning with cross-entropy between the target and the output of the network, you would need to sample this thing a lot, right? So if I have to sample this at every point of my application, and then I have to do tomography data basically over this output, that's not very efficient. So to implement this in an actual quantum hardware, you have to think very carefully about what your loss function is. I think that's the biggest challenge to actually use this constructively. Maybe to show you that overhead plot. See. Right. So this is what the training looks like. So the training steps are on the x-axis. The post-selection overhead is on the y-axis. These are 2 different tasks. This was the sequence learning task. So this was like 4, 4, 4, 4 versus 1, 2, 3, 1, 2, 3, and so on. This one is MNIST. And that's just a constant overhead. So how often would I have to do amplitude amplification at every step, at every neuron? And just to point out, this is not an overhead that I have to do recursively. So this just means at every point in time where I have a neuron, I'm applying a circuit that's not one gate deep, but like 100 or 10 or whatever that is. What's interesting is once you converge, so when the validation loss goes down, which is the loss function, the overhead shrinks in these very simple examples. And that's just because the prediction gets so good that, you know, the neuron kind of aligns to, you know, just give you that answer right away. The more complicated examples, the overhead tends to, you know, converge to some large but not huge value. You can prove upper bounds in this. So they're not drawn in here, but they're not really bad. Right. So I think there's no fundamental reason why you couldn't do that on a computer. Yeah. It's actually what I found interesting is as well that my first goal was to really do this and, you know, try to implement it in on one of the IBM computers and try, you know, to do a really trivial classification task. I was not at all expecting this to work for MNIST or anything that's large enough to even warrant, I don't know, a submission of journal or something like this. So I was quite surprised when I compared the same setup to one where I did not have the neurons. So where the order of the quantum neuron was, you know, not cos squared, but just cos and sine. So you have like very smooth activation. The training was really bad. So I really think that the structure, which people are also doing for VQE now, like I'm not saying this is like I came up with that idea to adding structure to variational quantum eigensolvers. By no means. People tend to, you know, make an ansatz that's kind of tailored to the Hamiltonian that you're interested in and things like this. So I think there's a lot to be gained to being a bit more structured in the ansatz state that you're creating. And the cell that I was proposing, I think, is relatively simple still. So you could maybe compare this to a traditional recurrent neural network like the first generation. You could make them much more complicated, right? You could dedicate a step to like memory, one to erasure, and so on. Would be interesting to see the performance of that.
Yeah, I was curious about the fact that you were able to simulate efficiently using, so I guess you used PyTorch. Can you comment a little bit of whether you played any tricks to be able to simulate these circuits efficiently, or are you just simulating the full state?
Full state. So I just had a state vector. I implemented the unitaries as tensors that you just, you know, contract indices. It's really quite efficient. So the unitaries, the only shortcut I took, as I said, was I did not do the quantum neurons as as actually implementing amplitude amplification. I just, you know, directly post select on that outcome. Yeah, no, I mean, this was literally like for 12 qubits or so. The matrices were 4,000 by 4,000. The state vector was 4,000 long. I did not use sparse matrices either, so they were full matrices. That was actually faster than using sparse matrices, I guess, because backpropagation through sparse matrices is not done that well in PyTorch. One thing I did though was if I'm applying, say, a single qubit unitary, you know, a parametrized single qubit unitary, I did not first blow that one up to make it a huge matrix, but that one was a 2x2 qubit, 2x2 unitary that I then, so my state vector was not a one-dimensional vector, it was a tensor with 12 indices. So that's the only, I think that's quite standard, right? I mean, if you write a quantum simulator, MPS simulator or so, you use a tensor library. I just used PyTorch as a tensor library, essentially.
Cool. That's interesting. One thing is that that maybe is relevant and kind of for a separate discussion, but I guess to get derivatives of that, you presumably use automatic differentiation in PyTorch. Our group actually has some work on automatic differentiation for tensor code for if you want higher order derivatives. So if you want parts of the Hessian, PyTorch is not very good at this, and we have code that is.
Okay.
So there's a tensor structure and allows you to do like alternating optimization and quadratic methods.
Interesting.
So maybe
is your code based on what tensor libraries is emulated?
It interfaces to a bunch of different things, to kind of both TensorFlow like code, as well as standard NumPy INSUM, as well as distributed tensor contraction library, which our group.
Okay.
So if you
that would be really interesting.
Yeah, the library is called AutoHoot. It's available on GitHub. I can quickly send.
Yeah, that'd be cool. Yeah.
On chat. Yeah. Cool. But yeah, I guess we should wrap up the seminar. We're by this point 20 minutes over time. Thanks everybody for the question and discussion. Are there any final questions? I guess at this point. Okay. But yeah, and thanks Johannes for sticking around and for
thanks again for the invitation.